Chapter 5 takes a look at continuous random variables. In Chapter 4 we looked at discrete random variables where we were working with the Poisson distribution, the geometric distribution, and the binomial distribution, where each one of those we were interested in the probability that x was equal to a specific number or less than or equal to a specific number, and everything was in whole numbers essentially. We wanted 7 successes. We weren't interested in 7.5 successes. Or we wanted to know how long until the first success. We weren't interested in how long until the 3.2 success. That wouldn't make sense. But some data is continuous. Data that's continuous can take on any value in between the numbers. And that's what we're going to look at today, is how do, the essential question, how do PDFs, which was probability distribution function in discrete case, work for continuous data? And PDF actually means something slightly different when we're talking about continuous probability distributions. PDF with continuous functions are thought of as probability density functions. And you might have noticed in Chapter 4 several times I said density on accident instead of distribution, because they both have the same abbreviation of PDF. It's just density if we're talking about continuous, distribution if we're talking about discrete. And basically a probability density function is not interested in the individual probabilities at points, but rather it starts thinking about the area under a curve. The idea here is going to be, we'll have some curve, maybe this guy. And if we looked at all of the area under the curve, the entire area would equal 1. So if you counted all that area, it's equal to 1. And so if you don't have all the area, you've got some percentage or probability of the area. For instance, trying to copy the same function here, not too well, but we'll go with it. Let's say I was interested in the probability that x was less than some number x. So here's x. If we wanted the probability that we were less than that, we would take the area to the left. Similarly, if we wanted the probability that our random variable x was greater than some number x, so here's the curve, and let's say x is over here, greater would mean we would want the area to the right of that number x. In fact, we could even tweak it a little more, and we could say, what if, there's my probability density function, what if I wanted the probability that our random variable x was between an x1 and an x2? So x1 here and x2 there, we're interested in the area that comes up in between. That's the idea of a probability density function. The big idea is that the probability is equal to the area. Probability is area. So to kind of set this up with an example, let's say I have a probability density function here that looks like this. Let's say there's 1 and there's 2, and the entire height of the thing is 1, which means the height at 1 is going to be 1/2. We could fill in some values. 1.5 here. The height there is 0.75. Let's just do decimals instead of fractions. So you can see we've got a triangle here. If we think about the entire triangle, the height of the triangle is 1. The length of the triangle is 2. And we know that area of triangles is 1/2 base times height, or 0.5 is the half. The base is 2, the height is 1. Notice the entire area of this triangle is 1. If the area is equal to 1, then we have a probability density function. This one doesn't have a lot of application, but the formulas are easy enough for us to understand the concept of how probability density functions work, how probability is area. Let's say, and I'm going to try and color code this to make this easy. Let's say, we want the probability that x is less than 1. Well, that would be from 1 going down. Notice that's a triangle. So probability is the area of that triangle. Get that 2 out of the way so it doesn't confuse us. So the height of, so we've got probability of a triangle is 1/2 times the base. Notice the base has a length of 1 times the height, which is 0.5. And 1/2 times 1 times 0.5 is 0.25. So in this case, the probability that x is less than 1 would be 0.25. What if I want the probability that x is greater than 1? One way we could do this is say, well, greater than 1, that's everything to the right of 1. We could take 1 minus 0.5 and get 0.75. Or we could use an area formula. You might notice that is a trapezoid sitting on its side. You might need to look up the trapezoid formula, but the trapezoid formula is 1/2 times the height, and the height connects the 2 right angles. So the height here is between 1 and 2. The height is 1. Times the sum of the bases. Those are going to be the vertical parts here. So at 1, the vertical distance is 0.5. At 2, the vertical distance is 1. So we have 0.5 plus 1. And again, that's just looking up the area of a trapezoid formula. And when we type that in our calculator, 0.5 times 1 times 1.5, we do get 0.75, just like we would expect. Because probability is the same thing as area. Probability is area. That's the big idea today. We could even do a conditional probability. Let's say find the probability that x is less than 1, given x is less than 1.5. So now we are only interested in the less than 1.5. We have a given probability. Well, the way we do that is we do the probability of both divided by the probability of the denominator. Well, both, we want to be both less than 1 and less than 0.5. So both is going to fall into the just less than 1. So triangle is 1/2 base. The base is 1 times the height. The height is 0.5. Over the bigger triangle that I outlined. That's the less than 1.5. That's the given information. That's also a triangle. 1/2 times the base, which is 1.5, times the height, which we see is 0.75. Nice, the 1/2s divide out, so we have 0.5 divided by 1.5 times 0.75, and now we get a probability of 0.4444. So the way we calculate probabilities with continuous functions is we find their area. Now, the easiest probability distribution function to work with is called the uniform distribution. In the uniform distribution, all results are equally likely. The idea is we're going to have a graph that looks like this, and we'll have some minimum value A and some maximum value B, and because all results are equally likely, we're going to end up with a rectangle. And the height of this rectangle all the way down will always be 1 over B minus A. In fact, that's the function for the probability distribution function, or the probability density function. I'm saying the wrong one the other way, is 1 over B minus A, because that will always be the height of this rectangle. And that makes sense, because if we find the area, the entire area, the distance from A to B is B minus A, that's the base, times the height, 1 over B minus A. Those divide out, and it has an area of 1. All probability density functions must have an area of 1. Other important information, mu, the average, is just the average of the extremes, A plus B divided by 2. Sigma, the standard deviation, is the square root of B minus A squared over 12. Notationally, how we represent the uniform distribution is we use the random variable x tilde, a capital U for uniform, and then A, comma B, the low, comma, high value. So let's see if we can take this information and help us calculate some probabilities with the uniform distribution. Turns out the amount of time an 8-week-old baby smiles is uniformly distributed. Between 0 and 23 seconds. What would the probability density function be for the time an 8-week-old baby smiles? Well, we said our f of x is 1 over b minus a. 23 seconds, the maximum is our b, 0 is the a. So 1 over 23 minus 0, or just 1 over 23. In other words, the graph of this function has a height of 1 over 23, and it goes from 0 to 23. That is the density function. So what is the average length of time an 8-week-old baby is going to smile? Well, the average, we said, was a plus b divided by 2. So 0 plus 23 divided by 2, the average is 11.5. Average baby at 8 weeks will smile for 11.5 seconds. What about the standard deviation around that 11.5 seconds? Well, the standard deviation formula was the square root of b minus a, 23 minus 0, squared, divided by 12. And if we put that in our calculator, that's 23 squared divided by 12. Take the square root of that, we get 6.64. So 8-week-old babies smile an average of 11.5 seconds with a standard deviation of 6.64 seconds. So it's pretty spread out, actually. Let's find the probability that the baby smiles between 2 and 18 seconds. What we're asking to find is between 2 and 18 seconds. Actually, let's make this a different color. So we want the area between 2 and 18. Well, it's a simple rectangle. It's base times height. The base is between 18 and 2. 18 minus 2 is 16. The distance on the base is 16 times the height, which is 1 over 23. And when we do that on our calculator, we get a probability of 0.6957. So almost a 70% probability that a baby at 8 weeks old will smile between 2 and 18 seconds. Because probability is area. We can even work backwards here and find something like the 80th percentile. Let me clear out my picture here. 80th percentile. What we're looking for with 80th percentile is we want the point where the area beneath it is 80%, or 0.8. So, again, it's just an area formula. The length, we're going from 0 to x, so x minus 0, or just x, times the height, which is 1 over 23, equals that area I want of 0.8. This is just an algebra problem. Clear the 23 by multiplying both sides by 23. And x is equal to 0.8 times 23, 18.4. So 18.4 seconds. 80% of babies smile less than 18.4 seconds. We could even do a given probability. We're going to find the probability that more than 12 seconds, knowing she smiles more than 8 seconds. So what we're really asking to find is the probability that x is more than 12, given we know that x is more than 8. So I'm going to clear out my box here again. Trying to keep it all on the same screen, just barely getting it in there. So we want the probability that we're more than 12 seconds. So here's 12 seconds. We want this probability given that we know it's more than 8 seconds. So we're going to cut off the box and just consider from 8 seconds on up. I have to do some scrolling to get this done. So we want the probability of both, the probability that we're more than 12 and more than 8. Well, that's just from 12 to 23. 23 minus 12, that height, or that base, I'm sorry, is 9, times the height, which we know is 1 over 23, over the probability of the denominator. I'm sorry, the probability of the given information. We're given that x is greater than 8. So now we're just going from 8 to 23. To get that distance, 23 minus 8 is 11. Nope, 15. Yep, 15. So we have 15 times the height, which is 1 over 23, and that's nice because the height divides out, and we're left with a 9/15 probability, which is 0.6. So if a baby smiles more than 8 seconds, there's a 60% probability she's going to smile more than 12 seconds. That's the uniform distribution. In fact, let's do one more uniform distribution example. Let's say the time it takes a kid to eat a donut is between 0.5 minutes and 4 minutes. And let's say we know it's uniformly distributed. It's not more likely for them to eat it at any one time than the other. Then f of x, our distribution function, is going to be 1 over b minus a. Remember, b is the maximum, a is the minimum. So 1 over 4 minus 0.5, the function is 1 over 3.5. And that's an ugly decimal, so let's just leave it as 1 over 3.5 for our example. So now we're going from 0.5 to 4, and the height is 1 over 3.5. So the average, the mean, is just going to be the average of the extremes. 4 plus 0.5 divided by 2. And on the calculator, 4.5 divided by 2 is 2.25. So the average donut is eaten in 2.5 or 2.25 minutes. The standard deviation, remember standard deviation is the square root of the difference, 4 minus 0.5 squared divided by 12. And so we've got the square root of 3.5 squared divided by 12. And the standard deviation here is 1.01 minutes. So what is the probability of at least 2 minutes? At least 2 minutes. What are we asking for there? We're asking the probability that our x is bigger than 2, at least 2 minutes. So from 2, we want the area above that. So the base is 4 minus 2. The base is 2. The height is 1 over 3.5. Base times height is the area of the rectangle, 0.5714. Just over a 57% probability it's going to take at least 2 minutes. What about the probability it will be at least 2 minutes, knowing it is less than 3 minutes? What are we asking for there? The probability that it's at least 2, bigger than 2, knowing or given that x is less than 3 minutes. So we're only going to be interested in 3 minutes down for calculating our probability. Well, we get that by finding the probability of both divided by the probability of the given information. That's conditional probability. The probability of both is this area between 2 and 3. Well, the length there is 1. times the height of 1 over 3.5 divided by the probability of the given information. The given information is less than 3. So we're going from 3 down to 0.5. 3 minus 0.5 is 2.5 times the height, which is 1 over 3.5. And as usual with conditional probability, there'll be some reducing. And so we have 1 over 2.5. Now the probability is 0.4, or 40%. Let's do one more percentile problem, too. Let's find the 30th percentile. When we're finding the 30th percentile, we want to know at what point is the area between it, we'll call it x, at what x is the area below going to equal 30%, or 0.3. So the base, here the base is x minus 0.5 times the height, which is 1 over 3.5. And I want that to equal my area of 0.3. Now we just have to solve this formula for x. Clear the fraction by multiplying by 3.5 on both sides. And x minus 0.5 is equal to 0.3 times 3.5 is 1.05. Add the 0.5 to both sides, and you get 1.55. Just over 1.5 minutes is the 30th percentile. 30% of children will eat the donut in less than 1.5 minutes. So a shorter video today as we're practicing this concept of area being probability. Specifically working with the uniform distribution as we do that. We want to get really comfortable with this concept that area is probability before we get to the next chapter, which is probably the most important distribution that we're going to see in this course, the normal distribution. So let's practice with this. We're only going to spend a little bit of time in class on it, and then we will dive into the normal distribution. We will see you in class.